Hello, everyone. Welcome to today's Federal Interagency Committee for Indoor Air Quality, or CIAQ, meeting and webinar. Just a reminder, the audio for this meeting is through the phone only. I want to get started by going over a quick overview of today's agenda. I'm making a few announcements right now, and then we are very honored today to have Deputy Administrator Janet Mccabe and EPA Indoor Environments Division Director David Rowson to bring us our welcome and introductions, followed by a presentation on Ashrae's IAQ standards before, during, and after COVID, and then we will have our agency update. During the first half of the meeting, please feel free to use the chat function within the webinar to ask any questions or give any comments. And Dave, I will now hand it over to you.
Thank you very much, Lorene. Hello, everyone. My name is Dave Rowson. I'm the Director of the Indoor Environments Division in EPA's Office of Air and Radiation. And thank you very much for joining us today. We have a unique agenda for today's meeting, as Lorene has already mentioned. In addition to our regular indoor air updates and conversation across the federal government, we have two distinguished guests with us today who will be sharing some of the most current initiatives and guidance on improving indoor air quality and combating the spread of COVID-19 indoors. The Environmental Protection Agency's Deputy Administrator, Janet Mccabe, and Dr. William Bonfleth, Professor of Architectural Engineering at Penn State University and Chair of Ashrae's Epidemic Task Force. To get things started, it is my pleasure to introduce Janet Mccabe, the Deputy Administrator of EPA. Over the course of her career, Deputy Administrator Mccabe has worked for state environmental agencies in Massachusetts and her longtime adopted home state of Indiana, with a focus on implementation of the Clean Air Act and other outdoor and indoor air quality issues. Janet has also worked for Children's Health Environmental Health Advocacy organization based in Indiana. Prior to her current appointment, Janet spent 7 years as acting assistant administrator and principal deputy to the assistant administrator in the Office of Air and Radiation under President Barack Obama. Janet knows firsthand through these experiences that programs to improve public health and protect our environment are strongest when they are informed by a diversity of perspectives and rooted in science, transparency, and the law. Deputy Administrator, thank you for joining us today, and the floor is yours now.
Dave, thank you so much. It's such a pleasure to be here with this distinguished group and everybody who's listening in who is interested in and passionate about indoor air quality and public health. It is truly my pleasure to be back at EPA working again with Dave Rowson and the other incredible career civil servants at EPA who have dedicated their professional lives to these important issues. And an honor to be attending this meeting of the Federal Interagency Committee on Indoor Air Quality. This time around, as Dave said, I'm privileged and honored to be in the position of Deputy Administrator of the EPA. But during my previous tenure in the Office of Air and Radiation, I was able to be very close and personal with the agency's work on improving both outdoor air, ambient air quality, and indoor air quality. There are many issues in our world that affect our public health, but as one long ago mentor said, if it's in the air you breathe, it's pretty serious in terms of affecting our public health. I know and believe that strong cross-sectional collaboration and communication is key to successful policy implementation. I think that's especially true in the area of indoor air quality, where we don't have a big statute like the Clean Air Act to direct a lot of the work. This collaboration and communication is best achieved when we talk to one another and understand each other's work, each other's perspectives and challenges. And this Federal Committee on Indoor Air Quality does exactly that. It provides an ever so valuable forum for facilitating collaboration and communication, particularly with respect to the challenges we faced as a result of the pandemic over the last 2.5 years, which has brought indoor air quality into people's consciousness in a way that I believe it never had been before. Between the staggering death toll that has now surpassed 1 million lives lost in the U.S., the social and political tensions that the pandemic has caused and is causing, this country is going through a lot. I think many of us believe and understand that better days are ahead, but we're not there yet. The economy is opening again. Many of us are returning to schools, businesses, and workplaces with a sense of relief, with a sense of continuing anxiety, with a sense of uncertainty about how much longer this will go on, how many more surges there will be in the future, and understanding that we need to think about that with respect to these schools, businesses, and workplaces that we are returning from. But I'm optimistic in part because this administration has been taking clear steps to address the current and future challenges of this virus, including recognition of the role that indoor environments have in controlling the spread of the virus and other contaminants. As I said, in my experience, there has never been this kind of attention on indoor air quality from the highest levels of government. And given the amount of time we all spend indoors in homes and workplaces and schools, particularly that our children spend in schools and daycares, this attention is appropriate and welcome. In the public and private sectors, experts in indoor air quality and public health professionals are more than ready to go to be pushed forward by this high-level interest. As part of President Biden's National COVID-19 Preparedness Plan, EPA issued the Clean Air in Buildings Challenge in March of this year. Throughout the pandemic, building managers and facility staff have been on the front lines, implementing approaches to protect and improve indoor air quality, to reduce risks, keep their occupants safe and healthy, and we are so very grateful for their efforts. The Clean Air in Buildings Challenge is both a call to action and an important tool that presents options and best practices for building owners and operators. The challenge highlights a range of recommendations and resources that are available to assist with improving ventilation and indoor air quality, which can help to better protect the health of building occupants and reduce the risk of COVID-19 spread. EPA and the White House COVID-19 response team consulted with the Centers for Disease Control, the Department of Energy, and several other federal agencies to develop the Clean Air in Buildings Challenge, a collaboration on indoor air that began with the work of groups like this one. And while Dave will cover this in more detail, I want to mention the key actions outlined in the Clean Air in Buildings Challenge. Create a clean indoor air action plan. Optimize fresh air ventilation. Enhance air filtration and air cleaning. And conduct community engagement, communication, and education. These recommended actions cannot completely eliminate risks, but they will reduce them. EPA continues to provide technical assistance to promote better ventilation infiltration in schools, as it has done for many years. Most recently, the agency held a webinar with experts from the University of Colorado at Boulder, their Integrated Bioscience and Built Environment, the Integrated Bioscience and Built Environment Consortium, and Boston Public Schools to discuss how to implement cost-effective, comprehensive indoor air quality monitoring and how to optimize ventilation and HVAC systems to prevent the spread of COVID-19 in schools. Over the past 2 years in particular, EPA has provided guidance, webinars, and technical advice, including through a series of webinars for school administrators and facility managers to help schools open and stay open as possible during the pandemic. American Rescue Plan and bipartisan infrastructure law funds can be used to supplement investments in ventilation and indoor air quality improvements in public settings. Indoor air is not only a COVID-related priority for EPA. It is an important priority for EPA because of the breadth of its impact on public health. EPA's vision for environmental and public health protection is outlined in EPA's 2022 through 2026 strategic plan. This plan advances key goals for tackling the climate crisis, air, water, and land, environmental and public health protection challenges. The plan outlines key strategies and objectives for advancing environmental justice and equity, ensuring the scientific integrity of our work, and the consideration of children and other vulnerable populations in the work we do to advance environmental and public health protection. And in this plan, the administration has highlighted improving indoor air quality as its own unique objective for the very first time. You all and the work of this committee play an important part in meeting this vision. We all have questions about what the future holds, but no matter what, the efforts we take now to promote indoor air quality protections and solutions in our homes, schools, and workplaces will have a lasting impact on our nation's health and quality of life. So before I close and hand this over, I'd like to thank Dr. Bill Bansleth for also joining today's meeting to provide an important overview of Ashrae standards for normal operations in buildings and Ashrae's pandemic guidelines for use during disease surges. Early in the pandemic, Ashrae assembled a task force of leading engineers, building scientists, and other experts. This task force published seminal consensus guidance on how to optimize building ventilation and filtration practices. I'm so glad Dr. Bansleth can be here today to highlight what we should do to create healthy indoor environments with ventilation and filtration practices, and how we should be thinking of adjusting those practices to meet the ebb and flow of disease transmission that seems to be our new normal. So let me turn the meeting back over to Dave to highlight some particulars of the Clean Air in Buildings Challenge and its relationship to current EPA indoor air quality priorities. Thank you so much for having me, and I look forward to working with you on this critical public health issue. Thank you. Back to you, Dave.
Thank you very much, Deputy Administrator. As Janet outlined, the National COVID-19 Preparedness Plan issued by the White House on March 2nd of this year, among other advances in COVID-19 policy, highlighted the importance of improved ventilation, filtration, and other indoor air quality practices as a critical strategy for helping to mitigate the spread of COVID-19. The third section of the plan, which accompanied other sections focused on vaccination, medical treatment, and preparation against new variants, is focused on strategies to prevent economic and education shutdowns. And featured in this section is a new Clean Air in Buildings call to action from the U.S. government. This call to action includes 4 components: building awareness of the importance of good ventilation, filtration, and related indoor air quality practices to reduce the spread of disease, supporting state, local, and tribal governments and schools to make improvements in ventilation, filtration, and indoor air quality in buildings by making American Rescue Plan funding available to pay for such improvements. A set of high-level best practices issued by EPA, which Janet described, also in March, to support the Clean Air in Buildings call to action, a document called the Clean Air in Buildings Challenge Best Practices that helps guide areas of focus for building owners and managers, and a planned recognition program to further incentivize action in this area. As one element of EPA's involvement in supporting the White House call to action, we are sponsoring the delivery of a series of technical assistance webinars to highlight the importance of improved ventilation, filtration, and other indoor air quality action in buildings to help mitigate the spread of COVID-19 and other airborne disease now and in the future. In today's event, in which we're leveraging this existing CIAQ stakeholders network in this public meeting, as Janet mentioned, we're featuring a session on existing Ashrae standards that EPA has long promoted and affirmed for use in normal operations in buildings, and Ashrae's pandemic guidance that can guide these critical improvements in ventilation and indoor air quality in buildings, particularly during surges in the pandemic or other disease transmission. This, as many of you who have joined us know, many organizations in the federal government, including EPA, have long worked to promote such ventilation, filtration, indoor air quality improvements. The call to action by the White House is an opportunity for us to further advance these broad interests in improving indoor air in buildings as a critical component of improving public health in our nation. Today's webinar will in particular focus on these improvements to combat the pandemic and other disease transmission, but such improvements are also important in general for a wide array of efforts to reduce exposures to indoor air contaminants and other poor indoor air quality issues. We are very glad, though, to be delivering this session today. Very pleased that Deputy Administrator Mccabe kicked us off, and that Dr. Bill Bonfleth will be taking us through an overview and an engagement with Ashrae standards and guidance in this area. So let me turn the floor back over to Lorene Burton to introduce Bill. Thank you.
Thank you, Dave, and thank you, Deputy Administrator. It is such an honor for you to have joined us today. At this time, I'd like to introduce Dr. Bill Bonfleth, or William. He is a professor of architectural engineering at the Pennsylvania State University in University Park, Pennsylvania. He is a fellow of Ashrae, the American Society of Mechanical Engineers, and the International Society of Indoor Air Quality and Climate. As the chair of the Ashrae Epidemic Task Force, he has been recognized with a letter of appreciation from the U.S. EPA and the Ashrae Presidential Certificate Honor. At this time, I want to hand it over to Bill, who is going to tell us about Ashrae IAQ standards before, during, and after COVID. Bill?
So thank you very much for the invitation to be here today. There are many people on the call, I think, who I've known for a long time and whose contributions in this field I value very much. So,
Bill, before you get started, let me just remind people you can input your questions into the chat box at any time. Just don't want you to miss any good questions, Bill. Thank you.
No, that's always the best part. And I'm very honored to have the Deputy Administrator and to have Dave Rowson here today as well. I echo what the Deputy Administrator said about the importance of government attention. I've been saying for years that we'll get somewhere with indoor air quality when we have government, scientific, and public attention on the subject, and I don't think we'll have better conditions again than we have now. So this is the time to do something. My topic today is to tell you where we are with existing Ashrae air quality standards, and that's going to focus on one of them in particular that everyone has heard of, I think, Ashrae Standard 62.1. I also want to give the context of what we have recommended during the pandemic, which is not really Ashrae standards, they're recommendations, but they certainly stand in some relationship to existing standards. It's important. And then finally, some thoughts about where we might go from here. So again, these are our three topics, and without further ado, I tried to make a list of Ashrae indoor air quality standards, and I gave up before I got through all of the ones that could be on this list because there are quite a few of them, and maybe that's a revelation to many of us. The most important ones are the design standards, 62.1, 62.2, and 170 for non-residential, residential, and healthcare facilities. But we also see air quality standards for aircraft coming out of Ashrae, for mass transit facilities, and it's also something that is incorporated in high-performance building standards. And these standards are themselves supported by a large number of test standards and guidelines for things like rating filters and air cleaners and measurement methods. So there's actually quite a library of standards that are relevant to this subject. Standards are intended to be enforceable, mandatory information that can go into codes. Ashrae also has guidelines, and I've listed a few here that support the air quality standards. One for rail passenger vehicles, one that's a supplement on commercial aircraft. And there are several emerging guidelines. The P means that they are proposed, so they're all under development at various stages. One on enhanced indoor air quality that I think is almost ready to go. Another one for healthcare facility ventilation, and a third on protecting building occupants from wildfire smoke. So there's a large body of standard and guideline information put together by Ashrae's committees that can be accessed to address our common goals here. It is the best example and the most important example of these. I'd like to go through what's in Ashrae Standard 62.1, ventilation and acceptable indoor air quality. It used to be ventilation for acceptable indoor air quality, but the name was tweaked fairly recently. I think you'll agree when you get to the end of my summary that there's really a lot here that is exactly what we need to move forward, but I'll point out that one of the big issues we have is how much of what's in a standard actually gets into the building code and becomes mandatory for someone who's designing or operating a building. So we'll come back to that point a little bit later. You can see the main sections of 62.1 listed there on the left, purpose, scope, definitions, and others that we'll go through. And I'll touch on all of these things except for the appendices. So the purpose of the standard is to specify ventilation rates and other measures that will give us air quality that's acceptable to occupants and that will minimize adverse health effects. I'm going to pick on this point of minimizing adverse health effects as falling short of actually promoting health, and that's one of the areas that I think we can improve on. It's intended for regulatory application, primarily to new buildings, but also to additions to buildings that are large enough to require it, and also if there are significant changes in the operation of the building. It should be applied to existing buildings. And it also is intended to be a guide to improving indoor air quality in existing buildings, even if it's not mandatory. The scope is occupied spaces in buildings except non-transient occupancy dwelling units. In other words, residential buildings that are covered by standard 62.2. And it covers comprehensively ventilation and air cleaning system design, installation, commissioning, operation, and maintenance. And there are also requirements that we'll see for some contaminants, limited number of contaminants and their sources, including outdoor air, construction, and others. But one thing that's not covered in the standard is pathogens. What's excluded from the scope is smoking, which was removed a long time ago because it was concluded that we couldn't specify ventilation quantities for smoking that met the requirements of the purpose of the standard. It also doesn't apply to any patient care areas that aren't listed. Those fall under Ashrae standard 170 for healthcare, and likewise laboratories with hazardous materials. But it does cover really the majority of non-residential buildings and spaces in those buildings. From the definitions, I only want to pull out one thing, and that is this critical definition of acceptable indoor air quality, which ties back to the stated purpose. No known contaminants at harmful concentrations is determined by cognizant authorities, and a substantial majority of the people exposed do not express dissatisfaction. So I call this a safety and satisfaction criterion because from the health point of view, it only strives to prevent adverse health effects. It doesn't promote what we would call today health and well-being. And you may be familiar with the World Health Organization's definition of health, which starts out with the statement that it's not merely the absence of disease. So we have a standard that tries to avoid those adverse health effects and to ventilate at levels that don't cause occupant dissatisfaction. And you may have seen the data on the right, which has been the basis of these standards around the world for a long time, done by Fanger and others on human subjects that can relate the amount of ventilation per sedentary individual to the likely percent dissatisfied. So the next section of the standard deals with outdoor air quality. The ventilation standard must presume or specify how we can have outdoor air that's of acceptable quality to remove indoor contaminants. If we have outdoor air that's dirtier than the indoor air, then we may actually be making things worse by using it. So these are requirements for the outdoor air, and they fall into two categories. The first is regional air quality. So the user of the standard should determine whether regionally the outdoor air is in compliance with the national standards. In the U.S., that would be the National Ambient Air Quality Standards. And if there's non-attainment in some respect, then that can trigger special requirements. And in Standard 62, those relate to particulate matter and ozone. And also, the standard says that there should be a local air quality survey, so an observational survey where the building is located to identify potential problems, for example, sources of dust, smoke, or other emissions, which often happens in urban or even in rural agricultural areas. The next section deals with systems and equipment and the design of systems, and I will not go through all of the things I've pulled out and put on this slide, but I think it's important to note that there is a lot in Standard 62.1 about how you put together a system that is going to be able to deliver good air quality consistently, and this includes things like having a system that can be maintained and balanced, and taking care about where exhausts and outdoor air intakes are located. With respect to air cleaners, we're now starting to see requirements in the standard, like the one shown here, that air cleaners must be compliant with UL 2998, which essentially means that they produce no ozone. And related requirement, UV devices can emit no 185 nanometer UVC, which is a wavelength that produces ozone. And there are others as well that I would direct you to the standard to read in detail. This is the sort of thing that doesn't make it into the codes, as we'll note again later. Now, the part of the standard that most are familiar with, and it's probably the only part of the standard that many designers are well aware of, is the procedures section. These are the compliance paths by which we determine how much outdoor air has to be brought in to achieve the goals of the standard. The first procedure is the ventilation rate procedure, or VRP. It's a prescriptive procedure in which outdoor airflow rates are specified based on the space type, on the floor area of the space, and on the number of occupants. So if a designer has applied this procedure correctly and determined the total outdoor airflow that needs to be brought in, then they've complied prescriptively. The second procedure is the indoor air quality procedure, which relates to control of specific contaminants to required levels. This part of the standard has just been completely upgraded in a way that I think is very good and an important improvement. In the past, it was left to the user to identify the contaminants of concern and to do mass balance calculations to determine how much outdoor air was needed for control, and they could also apply air cleaners, but there was no requirement for verification of that. Now, in the updated standard, Addendum AA, which you can find at the Ashrae website, there are now specified concentration limits for what are called design compounds. These are chemicals and also PM 2.5 and several mixtures of the design compounds as well. And there's a new requirement that there be objective verification post-construction that the contaminant limits have been met. And there's also a requirement for a subjective evaluation to confirm that the occupant satisfaction required is achieved, and that's now been specified as 80%. So this has been made totally consistent with the definition of acceptable indoor air quality that we looked at a few slides back. There's also a section on natural ventilation. Those systems can be prescriptive or engineered. The standard doesn't address the engineered systems. It provides some prescriptive guidance regarding size and location of natural ventilation openings. And this can be applied to free running or hybrid systems. And generally, it is the least used of the three paths, I would imagine. And by far, the ventilation rate procedure is the one that's used the most. So the ventilation rate procedure begins by defining the required breathing zone outdoor airflow. So this is outdoor air that's brought into the part of a space where occupants are and where they will be able to actually benefit from it. The breathing zone is defined as 3 to 72 inches above the floor and more than 2 feet from the walls. And as you can see by the equation here, the breathing zone ventilation rate is the sum of two parts. One is a rate per person multiplied by the number of occupants, and the other is a rate per unit of floor area multiplied by the area. And so those two together become the design maximum breathing zone ventilation rate. This is an excerpt from the table where the various rates are found. It goes on for several pages, so I just grabbed a little piece of it that shows office buildings. You can see there, hopefully, the office space, for example, has a requirement of 5 CFM per person or plus 0.06 CFM per square foot. The population of a zone can be determined by the designer if there's a chair count or if the architect has given them a number, but in the absence of that, default occupant densities have been provided that can be used to give us typical values. I think with the default occupant density for office space, we wind up with something like 17 CFM per person, but I think it's important to point out here that there is no consistent CFM per person or CFM per square foot across all space types, and that becomes important when we get into discussions like we've had during the pandemic of what should the CO2 concentration be in a space. To comply with standard 62, it may be necessary in some cases to have a CO2 concentration that's well under 1,000 parts per million, but there are space types with high occupant densities that may have CO2 concentrations that are around 2,000 parts per million when complying with the standard. So this has been an interesting issue to negotiate in discussing what we should do with ventilation for infection control. Now, to this breathing zone ventilation quantity, we need to make some corrections. It's assumed that the outdoor air that's brought into the breathing zone is thoroughly mixed, some would say well mixed in that space, so that contaminant concentrations are all averaged out. But for a variety of reasons, we don't have that kind of uniform concentration of contaminants or uniform distribution of outdoor air in spaces. Even with mixing ventilation systems like the one on the upper left here, we can get spots that get more or less air, and so we have stagnant regions where things collect. Stratified ventilation has become very commonly used and is believed to be a better way to provide outdoor air, and in some cases it is. And also we can provide outdoor air directly to where an occupant is, personal ventilation. So we need to make corrections for the type of air distribution and also for how well it's performing. And in addition to that, when we take multiple spaces and connect them together in a system, so we have 10, 20, 100 rooms on an air distribution system, we now have recirculation of air that was in one space that goes back to the others. And so we have differences in the amount of outdoor air required depending on whether we have or don't have recirculation. And I won't go through the details of that in this talk. The ventilation rate procedure also discusses dynamic or demand control ventilation. Demand control has generally been used for the purpose of saving energy. The reason that we do demand control in most cases is to reduce the amount of outdoor air so that we stay at the level of ventilation that's required by the standard and no more. And that is an interesting thing to realize, because it means that whatever our minimum standard is, we're making sure we never do any better than that if we can avoid it. So we can reset the outdoor air based on the current occupancy, and in some cases it can actually be shut off when a space is unoccupied and then restarted. The standard is not explicit in saying how demand control can be done, although it does imply that carbon dioxide measurements are acceptable, but it also mentions some criteria that need to be met. I think we can do demand control differently, and we'll come back to that at the end. Ashrae has just published within the last few months a position document on indoor carbon dioxide, and it addresses issues of the uses of CO2 in ventilation and for infection, risk management, and I would encourage you to take a look at that. If you haven't seen it, it can be downloaded from the Ashrae website. So these corrections that we're talking about are in the standard given in the form of zone air distribution effectiveness corrections, and we divide the breathing zone ventilation rate by or outdoor air rate by the air distribution effectiveness. So if the value of EZ is less than 1, that means that we have to exceed the amount of outdoor air that was given in the original table 6.1 that we looked at. And if it's a larger value, that means you've got better than well-mixed ventilation effectiveness, and we can reduce it. And the 3 categories of air distribution that we talked about, mixing, stratified, and personalized, are now all covered here. And you notice there's quite a range in these EZ coefficients. 1.0 would be perfect mixing, but for mixing systems, if they're performing poorly, if they stratify for some reason, or if we have short circuiting, then EZ could be as small as 0.5. And for a well-performing stratified or personalized ventilation system, the value of EZ could be as large as 1.5. So that further changes the picture as far as how much outdoor air we really need. And this really kind of encapsulates a very important issue, which is how well air is distributed in spaces, and then that's something that lies outside the standard, but it's an important topic for the future to try to achieve good air distribution. We've seen that to be a problem in many cases during the pandemic. So I mentioned the indoor air quality procedure before, and now we'll look at it in a little detail. There are 14 design compounds and 3 mixtures of those compounds, and also PM 2.5 that are listed. And as I mentioned, we need to have objective evaluation that those requirements are met. For perceived air quality, 80% or more of the occupants by survey need to be determined to be not dissatisfied with air quality. You can get the addendum from the Ashrae website at the URL shown here. Hopefully my slides can be made available to folks afterwards. So I've taken the key information out of the IAQP and put it on this slide. This is the list of contaminants that now have to be controlled in any building complying with 62.1 by the indoor air quality procedure. And 15 is a pretty small number compared to the number of things we might find in indoor air, but it's actually still a pretty large number relative to the things that we would like to be sensing indoor for control. So I think it's moving in the right direction, but we have some distance to go. But these are all identified as fairly common and hazardous indoor air pollutants. And we have design limits for all of them. Many of you, I'm sure, are familiar with these numbers. And note that almost all of them come from Cal EPA standards. There is two from the EPA that come from NAAQS for ozone and CO. And the others are from German standards, AGBB standards. The mixtures are handled like mixtures are in other contexts where we sum the ratio of the concentration to the design limit, and the sum for all of the components of the mixture has to be less than 1. So it's a fairly traditional approach to this. And keep in mind that the goal here is to provide the same level of air quality that's provided by the ventilation rate procedure. So just because this is a performance method doesn't mean that it has higher aspirations than the rest of the standard. All right, so that's section 6, which is what most refer to because that's what goes into the building codes. But construction and system startup and operation and maintenance are both included. So under construction and startup, the main thing is to prevent contamination of materials and to prevent the contamination of occupied areas if renovation is being done, and to do balancing and testing and document. Of course, this is very important if we think back to some of the indoor air quality disasters of decades past. In many cases, those were caused by poor protection of materials during construction. In the L&M section, there is a requirement to reevaluate the compliance of the building and its systems if there's a change of use or major modification. And I think very importantly, and again, often overlooked, is an O&M maintenance item list that includes minimum frequency. I've shown just a part of this over on the right-hand side. There are 31 different items that are included there. And those include, although it's not shown on this excerpt, verifying the minimum outdoor air that systems provide every 5 years at the greatest interval. Many of us had learned during the pandemic when surveys were done of portfolios of buildings that many of them were not meeting their minimum requirements, and in fact, many of them were found not to be able to meet them. So this is a really important part of the standard. And O&M documentation is also mentioned here. So that's what I want to summarize at a high level, what's in 62.1. Now to wrap this part up, a few thoughts about the relationship of standard 62.1 to the building codes. I think many believe that standard 62.1 is the building code, but actually standards are mandatory only to the extent that they make it into the code, and that's a different step, and it can be a pretty fine filter for what's in a standard. So few standards are adopted in their entirety as building codes, and in some cases only a little bit makes it there. The International Code Council is certainly the predominant writer of model codes in the U.S. And the International Mechanical Code covers in chapter 4 ventilation, and that section follows the ventilation rate procedure from whatever version of 62.1 was in force when the particular version of the model code was updated. So it doesn't really cover the outdoor air quality requirements, the system design requirements, the other compliance procedures like the IAQP, the construction requirements, or the O&M requirements that we just looked at. So it sets aside a lot of things that would be really important for designing the building well, and also for maintaining and operating it effectively over its lifetime. This map that comes from the ICC website shows the coverage of the U.S. by the International Mechanical Code, and somewhat like the coverage with energy standards and their compliance with Ashrae Standard 90.1, we see that we've got versions of the IMC all the way from 2009 through 2021 that are adopted in different states. So this is an important thing to look at, is how do we get the good things that are in some of the most important standards into the code that they'll actually be used. So now we'll move on to what Ashrae has done during the pandemic, and it certainly has been a big job and a very rewarding job for me to work with so many subject matter experts to put together what the Epidemic Task Force has done. I'm going to summarize all of that by going through a one-page list of recommendations that we call the core recommendations that were published early in 2021. The reason that we did that was that we wanted to have a concise list of our main principles that we could use to keep everyone on this big task force coordinated, and also to make it clear to the public and the users of the guidance what Ashrae was recommending at a current particular point in time, and communicate the basics of airborne risk reduction. It really has been a big problem over the 2 years of the pandemic to make it clear in an ongoing way what Ashrae has recommended. I think everyone, not just Ashrae, early on was very conservative and proposed just about anything that seemed like it might help. But after only a few months, we were making significant revisions to the initial guidance based on considerations of technical feasibility and energy use and operating costs, and also reevaluating how much benefit there might be from some of the things that were recommended. And what I think we came to eventually, and this is really the current state of the guidance, is recommendations that support a flexible approach to risk mitigation that can be adapted to just about any building and situation. And again, these are advisory. They don't supersede standards like 62.1, and we had to give a lot of assurances to the standards folks that we were not writing new regulations that everyone would have to follow after the pandemic, although we hope that what we have done will certainly inform what's done in the future. So the first thing that I want to highlight here is the notion that what we can do with building systems, with building science solutions, is just one slice in the stack of slices of Swiss cheese, if you prefer that model of risk management. And it's just one layer in the hierarchy of controls that you may have been more familiar with previously from NIOSH, and not the most effective layer. Elimination, substitution are clearly always the best way to deal with a hazard. So we start the recommendations by saying follow public health guidance. And of course, that can be difficult as it goes back and forth under the influence of various forces, but by and large, public health guidance has been on target in terms of things that we should do. And so we encourage that those measures, like using masks when recommended, social distancing when recommended, being vaccinated when vaccines are available, are really the first line of defense, and will be complemented and supplemented by what we can do in buildings. The figures on the right here show a couple of good things about masks. One is that they shorten the range of travel of respiratory jets that may be very concentrated, and in the upper figure we see that the effect of masking, even if it's not very efficient, can be to substantially reduce the exposure, emissions by infected individuals, and exposure of susceptible individuals. So the meat of the recommendations is probably the ventilation, filtration, and air cleaning section. We start with outdoor air. The recommendation at this point is to provide and maintain at least the required minimum outdoor airflow rates per code and standard. The reason that's important is that early on there were a lot of sources recommending maximizing outdoor air. Whatever your system can provide, if you can go into full economizer mode, then do it, and that's going to be better. We don't think that that's really the right approach anymore. It's clear that it's energy intensive and expensive in terms of operating costs, and it has potential negative impacts on indoor environmental control and quality that should not be overlooked. And also, as we delve more deeply into what could be accomplished by other means, we found that other controls could be equally effective and more acceptable, both in terms of energy use and cost. Code minimum ventilation should be mandatory for general air quality control. We'll point out later, though, that doesn't mean that it's enough by itself. For filtration, we've recommended to use combinations of filters and air cleaners that achieve MERV 13 or better levels of performance for recirculated air. Filtering outdoor air doesn't help us with infection control because the pathogens have their sources indoors. So this applies to recirculated air. The Ashrae standard 62.1 only requires a MERV 8 filter in an HVAC system when there is a wetted coil or other wetted airstream surfaces. So it's actually a requirement that's related to the potential for particulate fouling of equipment, and it's not tied to exposure to particulate matter of occupants. And when we look at the performance of MERV 8 filters in terms of particle size removal, they're not very good for particles that are in the size range that we're concerned about. So the importance of this recommendation is that standard filters don't do much for infectious aerosols. Also, by saying that MERV 13 is okay, we're saying you don't need to go to HEPA, which was something that was suggested in a number of cases early on. You may remember that at one point the state of New York was thinking about requiring HEPA filters in malls, which was really something that was not feasible at all. MERV 13 has good efficiency for respiratory aerosols, and the combinations of filters and air cleaners language here allows for trade-offs with other technologies if a MERV 13 is not strictly feasible. So 2 filters in series with the efficiency of a MERV 13 or a lower efficiency filter and some other type of air cleaner could also meet this requirement. So brief reminder on how mechanical filters work. There are several different removal mechanisms. Impaction and interception tend to be more efficient at large particle sizes, so that's the curve that goes up to the right in this figure that I'm pointing at. And diffusion gets more effective as particles become smaller because random motions of particles become larger, so we have another component that goes up and to the left, and so we have a combined filter efficiency curve that has a dip in the middle. I think that filter performance was frequently misrepresented in popular accounts as always getting worse as the particle sizes get smaller. And we've tried hard to overcome that misconception. So filters are rated by another Ashrae standard, 52.2, and that standard only tests from 0.3 microns up, and it rates filters in 3 different size ranges, and the minimum efficiency in each size range from multiple tests is used to determine the rating. So there are numbers from 1 to 16, and the larger the MERV number gets, the more efficient the filter is and the better it does with fine particles. I've already mentioned that in 62.1, MERV 8 is the minimum requirement now. In Ashrae 62.2 for residential buildings, it's only MERV 6. So we're at a pretty low level. You can see from the representative filter efficiency curves here that down here between 0.3 and 1 microns, MERV 6 and 8 aren't very good, and big improvement if you go up to MERV 13. So that's important because if we look at respiratory aerosol size distribution, there are a lot of particles down in the PM 2.5 range, and the viruses themselves are in the fractional micrometer range. So I've overlaid here the filter rating ranges on respiratory aerosol spectrum, and we see that if we have filters that are low efficiency in ranges 1 and 2, which MERV 6 and 8 are, we don't do very well. MERV 13 is 50% efficient or better in range 1 and 85% or better in range 2, ergo the recommendation to use higher efficiency. You may be aware that California has already implemented a requirement for MERV 13 minimum for all buildings, residential and non-residential. All right, so now to this important point that code minimum plus MERV 13 may not provide adequate risk mitigation. It's been a problem throughout the pandemic to say exactly how much is needed. That rests on risk assessment that is difficult to do accurately, but it's clear that in some cases additional controls are required to meet the goals that we might have for making spaces safer. So how much uncontaminated air do we need? There are many opinions about this. WHO has published a roadmap on ventilation for COVID in which they recommend 60 liters per second per person for healthcare. That's 127 CFM per person, which is far beyond what's in 62.1, but not inconsistent with the total air change rates in some healthcare facilities. Alternatively, if you can't do that, 6 air changes per hour, which is probably quite a bit less, but similar to the lower range of air change rates that we would find in Ashrae Standard 170. For non-healthcare facilities, 10 liters per second per person has been recommended as a minimum. That's 21 CFM per person, and that's not actually a lot more than we find in many standard 62.1 compliant spaces, although it is higher. We don't have recommendations in 62.1, but if we go back to the 1914 ASHVE recommendations, and ASHVE was a predecessor organization to Ashrae, they were recommending 30 CFM per person at that time, even before the 1918 influenza pandemic, and that's 14 liters per second per person. And we also have various parties recommending 4 to 6 air changes per hour, which, as far as I can tell, comes primarily from analogy to Ashrae Standard 170, even though it covers an entirely different type of facility. And those should be considered minimums. Now, if we change the pathogen in the future, and we will have other airborne infectious diseases, then the amount of uncontaminated air it takes to dilute to get the same level of risk is going to change, and that's one of the problems we need to deal with in the future. We can't base all of our future standards on what happened with one pathogen, even though it was a bad one. A little more detail on the 10 liter per second per person idea. Hugo Lee, who's been working in infection control since the original SARS outbreak early in this century, has done analysis that suggests that if we can provide 10 liters per second per person, we can dilute the ambient air in a space to a concentration that's getting reasonably close to what it would be in outdoor air, and in the process also reducing the risk of short-range transmission. So this is one researcher's recommendation that's backed up by some good analysis, but it's not one that everyone agrees with, and I've seen much higher recommendations made as far as what is necessary in different environments. So now let's move on to the air cleaner part of this section of recommendations. Our simple, maybe cryptic recommendation is only use air cleaners for which evidence of effectiveness and safety is clear. Why is that? Well, while there are many air cleaners available in the market, there are many for which the manufacturer's claims are not well established by their own testing or by independent testing or by peer-reviewed research. Ashrae believes that in addition to mechanical filtration, germicidal ultraviolet is well established and not confident enough of where we are with other air cleaner types to give them the same kind of approval, though Ashrae does not recommend specific technologies or products. So at this point, the user who wants to use some of these other air cleaner types needs to study what's available and decide whether they believe that that is persuasive. We've seen mostly discouraging publications in the last 2 years when air cleaners have been tested. Not all, but a lot of it. And I've shown 2 examples of articles that have produced less than compelling arguments for the use of reactive species air cleaners. Now, one problem that we have with a lot of these air cleaners that are being promoted is that they put chemicals, disinfectants into the air, and so they don't behave like a filter. We don't have a single pass efficiency that we can assign to them, and so they're generally tested by doing pull-down tests. And if you wait long enough in a pull-down test, the concentration will eventually go to 0. So 99.9% inactivation over 3 hours may sound good, but it might have been 90% if the technology was turned off. So it's important to be able to convert that kind of data into an equivalent clean air sort of number, and there's a free tool available for doing that that's been developed by Elliot Gall at Portland State, and the address for that is shown here. So you can put in test data from pull-down tests and output a clean air delivery rate that is easier to interpret. Germicidal ultraviolet, the technology that has the best evidence basis behind it, damages the DNA or RNA of microorganisms when the most common wavelength is used, and there are other emerging technologies that may primarily damage proteins in the outer shells of viruses and bacteria, but the technology overall has been studied and applied for more than 100 years. It was used for operating room disinfection in the 1930s and also tested in school classrooms in the 1930s, and is approved for tuberculosis prevention by the CDC. The main source of germicidal UV is mercury vapor lamps, which are similar to fluorescent lamps, and they produce 254 nanometer UVC, which is very effective but not safe for direct human exposure. So there are some safety issues with applying it. LEDs and other types of sources like krypton chloride excimer lamps are making it possible to consider other wavelengths, and you've probably heard about far UVC that perhaps holds the potential of being much safer for use in occupied spaces. Germicidal UV can be applied that way by putting 254 nanometer fixtures above the occupied zone to create a disinfection zone. In terms of effective air change rates, 20, 30, even higher are achievable with this kind of system when there's good air motion in the space. They can also be put inside of an air handling unit and do airstream disinfection. Not as effective from that point of view, but it also keeps cooling coils and other surfaces clean. And portable UV for disinfecting contaminated spaces is also a widely used implementation of that technology. So as I said, it's been around for a long time. Wells and Wilder did studies in schools in the Philadelphia area in the 1930s, and here's an example of an upper room fixture in a classroom at the Germantown Friends School, and on the right the comparison between infections in the UV-treated classrooms in that school and the control classrooms. These are the same vertical scale, and you can see that at least in this study, there was a very significant effect. So as I said, different wavelengths are being explored, and a whole range of wavelengths work, at least within the UVC band. The figure on the left here from this paper by Ma et al. Shows everything from 222 nanometer far UV made by krypton chloride excimer lamps to 254 nanometer from mercury vapor lamp source to 280 from an LED, and they're all capable of achieving 3 logs of reduction, although in this case it appears that the far UV was the most effective of all of those that were tested. And there have been some chamber room size tests in recent times that have also shown that this technology can be effective in a somewhat realistic laboratory application. So those are the technologies we can add to ventilation and mechanical filtration. The next recommendation is that we should combine those various controls to achieve our risk mitigation targets while minimizing energy penalties, and I suppose we could add here minimizing the overall cost to the owner. This, I think, is one of the most important things that's come out of the development of Ashrae's recommendations, is that we look more broadly at different types of controls and combine them using an equivalent clean air delivery rate approach. This is what facilitates trade-offs, and it also allows us to recommend the overall control requirements in a simple way. What's the equivalent clean air delivery required, and then we can meet that by using different technologies. But I have to emphasize here that, as I noted when we talked about how much outdoor air is needed, there really isn't consensus on what these targets should be at the moment, and many are calculating their own or appealing to various authorities for them. So how do we do that? Well, we have dose response models for infection. The Wells-Riley one is the most used, maybe not the most accurate, but it's been well used during the pandemic and relates the source strength, the number of infectors, and the rate at which they're producing infectious doses, and the uptake by occupants, their breathing rate and time of exposure. So this is the dose, and the dilution, the uncontaminated airflow delivery, and that gives us an estimate of the risk of infection. So we can take this equation and we can substitute for uncontaminated air in the denominator here multiple terms that relate to different controls, and so we can have a Q that's an equivalent Q that combines outdoor air, filtered air, disinfected air, and even other removal mechanisms. We can take credit here for the effect of humidity and increasing an activation rate, or deposition of particles, for example. But we have to keep in mind that this is all fairly uncertain. This figure shows the infectious Quanta data for SARS-CoV-2 that are generally used in these risk assessments. And we see that while there's a clear change in emission rate as we go from breathing lightly to speaking to singing or shouting, and that's maybe 1 or 2 orders of magnitude. If we look at the range for any given activity, it's an even wider range. So to use this data, we generally make a fairly conservative assumption as to what percentile we're at, and we design for a super spreader type of emitter. And there are data for other types of pathogens as well that fit into the same model. So to follow up on this point about combining controls, more outdoor air often is not the best solution. In 2013, Lazimi and Stevens at Illinois Institute of Technology did an analysis of influenza using the Wells-Riley model, and they compared the effect of increasing filtration with the effect of increasing the outdoor airflow rate in different climates. And what you can see here quite clearly is that increasing filter efficiency, at least down to about MERV 13 or 14, gives a significant reduction in risk without a big reduction or increase in cost. This is annual cost per equivalent air change. Always a lot less than the cost of increasing outdoor air. And we also notice here that at least in this analysis, that going beyond MERV 14 for the recirculated air in a building doesn't seem to give much additional relative risk reduction, which again supports a MERV 13 or 14 recommendation for filter efficiency. And there's an additional reason to think about higher filter efficiencies. This is the collateral benefits of improving indoor air quality that I think we need to emphasize. This study done by Montgomery et al. Looked at the annual morbidity and mortality benefits of increasing filter efficiency. So they looked at MERV filters from 6, which was then the 62.1 minimum, all the way up to 16. And for different outdoor air PM profiles, estimated from existing models, the morbidity and mortality costs. And you can see that we get maybe about a factor of 4 increase in going from a MERV 6 or 8 to a MERV 13 or 14. The effect is very large if you're looking at a location with dirty air like Delhi or Beijing. But even if we pick locations that are representative of major cities in Europe or the US, we're still getting a significant benefit from doing this. And this economic benefit is something we have to keep in front of decision makers when we are recommending that we perhaps invest more in indoor air quality. All right, so we'll move on now to air distribution, which is the closely coupled issue related to ventilation. Ventilation air is only helpful if we get to the right place effectively. So that's one aspect of air distribution. The other is that air currents can create risk in certain situations. So we looked at a lot of literature on what is effective for infection risk prevention, and somewhat surprisingly found that it wasn't the same types of air distribution that we normally think of as leading to good indoor air quality. In other words, the stratified systems that have been heavily promoted over recent times. So our recommendation was that unless there's a specific reason to use directional airflow that comes out of a risk assessment or for some other reason, that mixing without strong air currents may be the best solution. Of course, we were also thinking here that it would be hard to make air distribution revisions to existing buildings in a short period of time. So this I think of as being one of the most short-term of our recommendations. For existing buildings, if they're mixing well, then that's probably okay. The figures on the right here illustrate a couple of problems associated with air distribution. The upper one is a case study of a COVID transmission incident in a restaurant in Korea, and we had one person who was infected who was sitting here at the upper right, and their dinner partner, not surprisingly, was infected, but also 2 people who were fairly far away, perhaps 6 to 7 meters away. And this occurred over a period of 5 to 20 minutes. These people left the restaurant shortly after the infected person entered. And when we analyze what's going on here, we have a couple of VRF cassettes in the ceiling that are combining to produce a 1 meter per second or greater velocity jet that's carrying infectious aerosol from the infected person to the susceptible ones. So that's something we're trying to avoid. The lower figure comes from a pre-COVID article published in the Ashrae journal that Hugo Lee was involved in, and they were investigating whether stratified air distribution was appropriate for healthcare facilities, and concluded because of the potential problem from so-called thermal locking, where exhaled aerosol could become suspended in the air in the breathing zone, that they were not recommending it for use for infection prevention in healthcare facilities. So I think we have a lot of things we need to look at going forward to answer questions about air distribution that were uncovered during the pandemic, and it turned out we didn't know as much as we thought we knew. Even simple things like where do you put returns in mixing ventilation systems. About the only thing we're generally taught is avoid short circuiting, but actually we find that perhaps having multiple returns and distributing them more widely may actually have some benefits. So say lots of grist for research in the future. Ashrae's guidance also touches on humidity and temperature, and the recommendation is maintain temperature and humidity design set points. Why do we think that? Well, there's a limited ability to adjust occupied temperature set points, and if you look at the data on responsive SARS-CoV-2 to temperature changes that DHS published, we're making spaces pretty uncomfortable in the interest of somewhat reducing the active lifespan of SARS-CoV-2. So we don't feel that that's something that should be done. As far as humidity is concerned, yes, it also has a significant effect on the rate of activation, but it appears to be lower than the effect of other controls. The figure on the right is from some research in influenza from Lindsay Marr from several years ago. And we see in the lower circle here that inactivation is affected by relative humidity between 10 and 90%, varies quite a bit. But when we combine that with even 1 air change per hour of ventilation and expected settling, that we don't have a very significant effect in terms of overall removal. And if we increase the ventilation to 10 air changes per hour, we can hardly see the difference here that's associated with humidity. So in addition to that, there's the concern that some buildings cannot handle the levels of humidity that have been recommended, 40% or higher, without developing other problems, condensation and mold growth. And these systems can be expensive in commercial buildings. So we didn't recommend it as a prioritized COVID risk mitigation measure, but it's still not a bad thing. And we go back to the Ashrae handbook and to guidance that's been there since the 1980s. For a long time, Ashrae has recommended 30 to 60% relative humidity, and the original work that supported that recommendation by Arundel and Sterling actually recommended 40 to 60. So this is not a bad idea, and I'll say that I've humidified my house for more than 20 years, and I'm glad I did for a number of reasons. So those are some of the basic technology changes. We also have recommendations that relate to how we operate systems during the pandemic. And the first was to maintain the design ventilation rate during occupied periods. And again, this comes out of an abundance of caution that when you don't really know how much outdoor air is required to reduce risk to a reasonable or acceptable level, then reducing it at all becomes a questionable act. So the reason for this recommendation was in part to discourage the use of conventional demand control for energy savings during periods of high risk, and also to encourage running systems no matter who is there, not just the normal daytime occupants, but also the maintenance staff. A third reason for making this recommendation was that early on, many were saying run systems 24/7, and that clearly doesn't seem to be necessary when you look at how long it takes to clear a building of contaminants by various means. And so that leads to the recommendation with regard to flushing between occupancies. The final form of this is that when we need to flush spaces between occupied periods, operate systems for a time required to achieve 3 air changes of equivalent clean air supply. We can imagine cases in which you might have a group in a conference room, and another group wants to use it, or they're switching classes using the same classroom in a school, and being cautious, we don't want residual infectious aerosol from one group to cause infections in other groups, which has happened. So we need to allow some amount of time to clear the air. And if we have a space where the mixing of the supply air is good with the room air, then 3 air changes is enough time to remove 95% of the initial contamination. And so again, this is to clarify that you don't need to run systems 24/7. And in fact, running the system at the very beginning of the day and the very end of the day may not be necessary at all if there's a long overnight period during which aerosol will settle out or circulation through filters will remove it. And this illustrates, I think, the evolution of the guidance to try to make it as energy efficient and affordable as possible. We also need to be concerned about reentry. There was more concern about this initially than as the pandemic progressed, but we still have seen cases where reentry of contaminated air has caused infections from space to space. The figures on the right come from a study of a South Korean apartment complex where there was a cluster of infections vertically along open natural ventilation shafts. So these have no backdraft dampers, and stack effect can cause contaminated air from one unit to move into another. And there were, I think, 10 infections in this apartment building. So the importance for users of the guidance is that evaluating energy recovery devices usually leads to the conclusion that you can continue to use them. And Ashrae has produced the long document about how owners can do that. There are other reentry paths that should be evaluated as well. This is just a general caution and maybe not the most important thing we're dealing with at this point in the pandemic. And then the final recommendation is that systems be commissioned, verify that HVAC systems are functioning as designed. That seems like a pretty low aspiration, but it turns out that it would be really a big improvement if every building was at least meeting the code that it was designed for. We know that many existing systems are poorly maintained and not functioning well. Again, before the pandemic, a study was done by GAO on schools that found that HVAC systems were the #1 maintenance item. 41% of school districts had 50% or more of their HVAC systems that needed to be repaired or replaced. It's hard to determine how well a system is going to protect you if you don't really know how it's working. So I think this is a big issue for the future, is maintaining the performance of systems. So now let's turn from those recommendations of the Epidemic Task Force to how that blends with existing standards and with what we know about air quality generally. And I would say that we've certainly had evidence that there's a health and productivity deficit that has existed for decades. William Fisk at LBNL was publishing articles and reports 30 years ago that indicated that it was costing the U.S. hundreds of billions of dollars per year in lost productivity and in increased healthcare costs. We've found plenty of evidence that buildings are not maybe the main cause of risk during the pandemic, but they're certainly a significant one, and that's partly due to poor maintenance. And we've also found in trying to develop guidance that the retrofit options were quite limited in many cases, and so it's been a heyday for portable air cleaner makers because the only way to upgrade a lot of buildings is to plug things in. So what sort of future developments might there be in 62.1 and other standards? These are just my ideas on that. I think that clearly if we're going to have a standard that promotes health and well-being and the contemporary understanding of those terms, that we need to update the scope and definition of acceptable IAQ in a standard like 62.1, and that may be the hardest thing to do. Some prescriptive changes that might be made is to look at the way in which ventilation rates are determined and do it on the basis of a risk and cost benefit basis, somewhat like the way energy standards are being done. I think we need to consider filtration for recirculated air, not just to protect equipment in systems. And I think that prescriptive performance tiers might be one way to make it possible to define higher levels of performance than we have now. This is done in European standards. The GSA does it in P100. I think it's something worth considering for Ashrae 62. Moving towards performance-based controls, I think, is a good thing to do as well. Maybe we still have prescriptive ventilation rates, but perhaps overlaid with sensing for some key contaminants so that we really know what's going on. And PM 2.5, PM10 might be among those, formaldehyde and perhaps some other VOCs, and possibly even carbon dioxide. And I also think that procedures supporting effective integration of multiple controls are needed. We don't really address much besides ventilation and perhaps minimal particulate filtration in the code intended standards right now. I think that would be a definite way to improve them. And also consideration of other than normal operating modes. The ventilation and filtration requirements in 62.1 and in the building code are only for normal operation. We don't have provisions there. What do you do if you want to be prepared for an epidemic or you're in an area where there are wildfires? I think adding resilience as a dimension of those standards could be helpful as well. And better integration with energy standards, because it's going to be essential. We already are seeing the pushback on air quality, at least in the circles I move in, because of the concerns about the energy cost of doing better. So all those things would be great if we did them. That's version one of the future. The other is nothing happens, because there are a lot of barriers. The existing buildings are always a problem, and we do a good job of figuring out how we would do the next new building, but the solutions for the existing buildings are really the important ones. We certainly know, if we pay attention to what the public says, that the scientific justification for better indoor air quality is not persuasive to everyone, and if they perceive that as a cost without a benefit, then there's going to be resistance, and that ties into the fact that the economic justification, although it's been done over and over, doesn't seem to be understood widely enough. The problem of split incentives: who pays, who benefits? Somehow the costs and the benefits have to be shared, and there are many ways that we could do that, and that suggests perhaps the need for policy changes as well as standards changes, which many are averse to. I think it's time to think about a little regulation of indoor air that would really be beneficial to all of us. Lack of standards and certification for air cleaners is a big problem. They're one of the best solutions we have, but we also can't specify them with confidence yet. Workforce education, from designers to technicians to building operators, I don't think there's a high enough level of understanding of human factors and of how indoor environment affects people. And I think we have a job to do there, but if we do it effectively, then it actually creates new industries and new opportunities for the economy to grow. Within the design community, there's certainly a perception of increased professional liability. There are several people who are probably listening who have been in the discussions about whether we can say the word health in standards for indoor air quality, or whether that's simply an invitation for litigation. And then finally, again, is this concern about energy and environment, about climate change and indoor air quality improvements not being sustainable. I won't go through all of these items in detail, but I just want to say that I think there are a lot of technologies on the shelf that are well understood that we can use to have buildings that have better indoor environmental quality and that are also low energy. Some relate to ventilation, some relate to alternatives to ventilation like air cleaners, and also I think smart building technology has a role to play here, and a different approach to demand control ventilation that strives to maximize benefits to the occupants while minimizing energy and environmental impacts is something that we can start thinking about as technology develops. And then final thoughts, my last slide. We've certainly learned that our built environment hasn't functioned as well as we'd like it to protect us during the COVID pandemic. Certainly, people have played a big part in that too and how they behave, but buildings have some shortcomings that are now well understood. We also have older IAQ issues that have been waiting to be addressed, and I think now is the time to work on those as well as on making buildings safer when there's another epidemic. Adaptability of buildings is going to be a key to making this work. So I go back to my comments about resilience and the need to think about different concepts of control of systems. We don't always want to operate a school like a hospital, but maybe there are times when we'd like to approach that level of protection if it allows us to continue operating. To make progress requires a broad coalition, public, private, and also commitment and cooperation over a period of time. Even if I had all the right answers written down today, it would take years to implement them, and I encourage everyone who thinks this is something that needs to be done to buckle up, because it's going to take years to make significant changes of the type that we'd like to see happen. I think that what the White House, EPA, DOE, and others have been doing in recent times is really important, and commend them for that. And I want to say it's essential to the program that we're trying to embark on. I think we can change standards, we can change practice if we focus on what science tells us and if we set some higher objectives than we've had in the past. And with that, I'll conclude and be happy to take questions if there's time to discuss.
Thank you so much, Bill. This was absolutely great. We do have some questions, and I'm going to hand it over to Lindsay to ask you anything that we have.
Thanks, Laureen. Yes, we do have several questions that came in. The first one is, as a testing, adjusting, and balancing company, how will federal buildings and facilities teams procure outdoor air and ventilation, measurement, and verification related services?
That's one of the things we've been thinking about. Of course, I think you can obviously procure it if you have the resources to hire qualified individuals, and of course that raises the questions of how much is it going to cost, and how do we know that we have the right level of expertise available to do the work. And I think this is an area where some of the programs that have been discussed, for example, legislation that's been introduced to incentivize evaluations of buildings, will be helpful if it helps to start businesses doing evaluations and thinking about their indoor air quality. But it's also a potential role for, say, an appropriate level of regulation. I think that some periodic requirement to evaluate the systems in the building would be extremely helpful, and point back to the list of maintenance items and in Ashrae standard 62.1. That's kind of a checklist for periodically evaluating the condition of a building. So I'm not in that business, but I can see a path to it if we cooperate to make it possible.
Great, thank you. The next question is, what is your opinion on the COVID-19 strategies and recommendations on increasing ventilation rates and/or air changes above Ashrae 62.1 standard? Would these increased rates or air changes be something to be accommodated in building codes or mechanical codes? In what ways do you think building codes should respond to mitigate COVID-19 in the future?
Sure. Again, that's a great question, or actually set of questions. Hopefully I answered that in part by saying that I think that we should look at all of the tools we have available, and it's not necessarily the best choice to increase outdoor air above the minimum that we're supposed to have according to our design standards. Maybe filtration or ultraviolet or some other air cleaning technology.
Right. Regarding delays in code adoption, is there anything federal or local officials can do to encourage code adoption?
Well, the codes, of course, there are codes. The question is, how do you get the good stuff from the standards into them? And in my mind, having a national model for state codes would be very helpful. We have, for example, for energy, standard 90.1 as the standard for energy conservation that all state codes are supposed to comply with. Compliance isn't perfect, but most states have some version of 90.1 that they've adopted. If we had 62.1 with all of its shortcomings in some regards as the model for state codes, instead of just having them get the ventilation rates, I think we would be in a much, much better position than we are now in terms of achieving good air quality in buildings.
Thank you so much.
So
our next question is, can you please say more about thinking about the safety and efficacy of 222 nanometers UV? We are seeing this used much more now, and should we move away from 254 nanometers?
I don't think it's time to move away from 254. I think it probably will go away eventually, but 222 has been tested on in animal studies for skin and I think also eye irritation. I know of at least one human study on skin that indicated that it was much safer than 254. I'm not sure I'm ready to recommend widespread whole room use of 222, but that's a possibility. And if we do that, then we would get both surface and air disinfection. But it also provides just a much safer way to do upper room UV that might be applicable to lower ceiling spaces, for example. So, I think the industry will start moving towards it as it becomes affordable and the technology is better understood, and perhaps other wavelengths as well. There's a lot of interesting technology development going on, mixing wavelengths and other things that we could talk about.
Great, thank you. Our next question, not all HVAC filters use the MERV system. How can building owners or homeowners equate other filter efficiency ratings to MERV?
Oh, yeah, there are some commercial filter ratings that are used for residential. And then that's a good question. I'm not sure I have a good answer to that, but I think filter ratings themselves need some further consideration. As we found out that even 52.2 can be hard to work with in terms of understanding exactly what it's doing with respiratory aerosols. So every filter has a rating based on its minimum, but the filter curves for individual products can be shaped somewhat differently, and then the aerosol size distribution is also important. So I think that in general, we need to look at some of the issues that have been raised during the pandemic about what is the real efficiency of this filter for a specific type of contaminant, and that's going to take time to do. But I think it's an important issue because we're really just making our best estimates right now, even as far as the performance of MERV filters, unless they've specifically been tested on bioaerosols.
Great, thank you. Apologies for that audio interruption previously. The next question is, while Ashrae standards are wonderful for performance of HVAC systems, are there other standards for portable air cleaning appliances to measure performance or reduction of microbes such as SARS-CoV-2, especially since most childcare and homeschooling is done in home dwellings?
Sure, and of course, the Ashrae standards that we've been talking about are really the design standards, and they would relate to standards for specific types of air cleaners. And the one that's most widely referenced today is AHAM AC1, which is a particulate removal rating for portable air cleaners that produces the clean air delivery rate, or CADR metric. So that's been used a lot as a way of recommending air cleaners, and some are actually certified and some aren't. So that's one thing you can look for, is it actually a certified CADR value or not. And AHAM Association of Home Appliance Manufacturers just published another standard, AHAM AC5, that actually is a microbial test. And that's so new that I'm not sure exactly how we should interpret the results, but they're working on a test procedure. And Ashrae actually also has some test procedures in progress that will allow for testing of air cleaners in chambers. And that was really conceived partly because of the need to be able to test things like ionizers or gaseous hydrogen peroxide air cleaners, but could also be used for a standalone air cleaner.
Thank you. The next question.
In your estimation, there will be a switchover to a chemical, apologies. It's a difficult question to read. In your estimation, will there be a switchover to a chemical H2O analyzer to determine humidity levels in HVAC systems and to maintain set point in the near future?
Yeah, well, we already have, of course, humidity sensors that can be used to control systems. And in some parts of the world where humidity is one of the main contaminants they're concerned about, you can control humidity. Maybe the question is, should we also be sensing chemicals? I think, yes, we're moving in that direction, although it's been hard to identify which chemicals to sense. There are differing opinions about whether we should just measure formaldehyde or perhaps nitrogen oxides in the homes because there might be cooking emissions from a gas stove. So we need to define what the key things to measure are, and then we can certainly use sensors to control ventilation or air cleaners.
Thank you. Our next question, what type of testing are you recommending for reactive air surface treatment devices? Single pass, chamber? When you say pull down, is that checking for longevity of the treatment provided by the device?
Yeah, well, the standard testing for those, if you look at what manufacturers have done and what others have done who've been evaluating those technologies, is that you seed a chamber with a microbial aerosol, and you measure the concentration of, you sample to measure the concentration of active, say, phage, if you're doing like an MS2 surrogate, and then over time you take samples and you measure how much is still active. And so you have to do a control curve where you're not doing anything, and you're essentially measuring the natural loss rate from deposition and from inactivation of the microorganism or removal by ventilation if there's airflow, which there is in some of these tests. And then you do it again. You start and you reseed the chamber and you run the test again, and you get a different decay curve. And so you can use the rate of decay from each of those, from say the control and from the technology on curve, to determine what the rate of removal was by the technology. But you're generally getting it in air changes per hour, which is related to the size of the chamber, and tests have been done in everything from a shoebox to 1,000 cubic meter chamber, and that makes a big difference. Surface testing is done maybe differently. The same thing, there's a natural loss rate, and so you have to compare the loss rate with no disinfectant applied to what happens when it actually is. That's the kind of tests that are being developed now, or chamber tests for that kind of equipment.
Thank you. And we're coming close to time, so for our last question, I've been telling people, says this person, 3 to 6 air changes per hour for their buildings by HEPA air cleaners, a school with no outside air, or combining filtration and ventilation. Do you have a personal preference for an ACH figure to use in a typical space, such as a church, a school, or even an office?
Yeah, of course, it's kind of my opinion from having read a lot of the literature and played around with risk calculators, but I don't think that shooting for 4 to 6, if you can get there, is a bad thing to do. Now, that doesn't mean 4 to 6 air changes of outdoor air. I'm adding filters to do that, and if they're portables, HEPA makes sense, but they don't have to be. They could be do it yourselves with a high airflow rate and a moderately efficient filter. When you do the analysis, it looks like that reduces the risk a significant amount, maybe cuts the exposure by factor of 2 or 3. And I recommended it to a local school that it has an ERV that's right on the Ashrae 62.1 outdoor air, and we went through every space and figured out how much air cleaner they'd have to add to get up to 6 air changes per hour minimum for each space, and they did that, and they've taken other precautions. And last year they had, in a school with over 120 students, 5 cases of transmission that seemed to be traceable to the school. So that's a pretty good outcome, considering that's going through the Omicron wave. So there's some empirical evidence that seemed to work well.
Thank you. It looks like we have one last question. Can you please speak to the efficacy of measuring CO2 and reducing risk of virus transmission, and measuring humidity as well?
Well, to say there's humidity instrumentation is available, so you can measure humidity. The question is how important that is in the big picture of COVID risk mitigation. And I already forgot the first half of the question. What was the other part? It was humidity measurement and...
It was, can you please speak to the efficacy of measuring CO2 and reducing risk of virus transmission and measuring humidity?
Right. Yeah, CO2. Of course, CO2 really is mainly a tracer gas as we use it in buildings. So, yes, you can sense CO2 concentration and relate that to the outdoor air coming in, but it's a lot more complicated than people may think, especially when you have multiple space systems. The recommendations for CO2 concentrations that have been proposed are largely based on someone having done calculations with a model like the Wells-Riley model and shown that there's a significant relative risk reduction when you ventilate at a level that results in a steady state CO2 concentration of, say, 800 parts per million or 600. There are more sophisticated ways of doing this where you do a risk assessment that's based on how much air that someone else has exhaled are you inhaling, the rebreathed air fraction, and then when you combine that with the prevalence of the disease in the community and the emission rate and the activity level of people, you can come up with a CO2 concentration that corresponds to the risk target you've set. But it's really, in the end, still determining what the ventilation rate should be. And I would here, I think, to end the response, say, take a look at the CO2 position document I mentioned, because it does have sections in it on CO2 for ventilation measurement and CO2 for infection risk control. It has some value, but it's not a silver bullet by any means.
Thank you. So back to you, Lorene.
Okay. Thank you so much, Bill. We did get a couple of other questions that are a little more complicated that we will share with you, and if you do have a response, we can add them to our minutes.
Sure, I'll be happy to.
That would be online. Yeah, they would be a little too complicated to get into right now, but they are interesting questions, and we will share them. And like I said, if you can respond to them, we will add them to our minutes when we publish them in a couple of weeks.
Sure, happy to.
Thank you so much. This was so interesting.